recording at this time. Okay, so when we last left off, we discussed many synthetic methods and many reactions involving carbonyl addition or 1,2 addition. We've looked at cyanohydrin formation and acetal formation, which primarily centered around using carbon and oxygen-centered nucleophiles. We're now going to look at the nucleophilic addition of amines to carbonyls, and we'll talk about different cases of imine and enamine formation. Okay, so depending on the substitution of your amine, you get different carbonyl addition products. For example, primary amines add to carbonyls to form imines, while secondary amines add to carbonyls to form enamines. Now, one thing to note is that an imine can best be thought of as an aldehyde or ketone equivalent in terms of reactivity. So here is an example of an imine. They are electrophilic at the carbon, mildly nucleophilic at the nitrogen. An enamine, however, reacts very similar to an equivalent of an enol or enolate. So if we look at an enamine, can best be thought of as very similar to that of a carbon-centered nucleophile known as an enolate, where enamines are highly electron rich at this alpha carbon. Okay, so does everyone see how depending on whether we use a primary or a secondary amine for this carbonyl addition reaction, we observe either an imine in the case of a primary amine or an enamine in the case of a secondary amine? Does that part make sense to everyone? Does this idea make sense? Any questions so far?
Can you scroll down a little bit so I can see the top one, please?
Like here?
Yeah. Okay, got it. Thank you.
Perfect. So let's talk a little bit about the mechanism for how imines are formed. So in the first step, under mildly acidic conditions, though not too large of an excess of acid because our amine needs to be the free amine in order to be sufficiently nucleophilic, our first step is our acid catalyst. So our acid is catalytic. It's going to protonate our carbonyl oxygen. This activates our carbonyl and makes it a much more electrophilic species at the carbonyl carbon. From here, even weak nucleophiles, such as our primary amine, can attack our electrophilic carbonyl carbon. We generate this tetrahedral intermediate. Now, this is where things get a little bit interesting. In order to activate this alcohol as a leaving group, we have to initiate a series of proton transfers. This can be facilitated by water or other protic components in solution. So after a proton transfer, we've now freed up a lone pair on our amine, and we've activated our alcohol as a leaving group in the form of water. Now, just like we've observed previously in the mechanism for acetal formation, we can lose water. We can kick out water and generate this iminium species. Now from here, all we have to do is deprotonate our iminium species, and that gives us an isolable imine. And imine is an isolable reaction product, and they're stable outside of strongly acidic conditions. Does this mechanism make sense to everyone? Okay. So let's talk a little bit about one application of this imine formation reaction that we'll in fact see in laboratory today. And that concerns imine derivatives. So addition of amines with an atom containing a lone pair of electrons on the adjacent atom occurs very readily, giving useful, stable imines. Classic examples of this include structures known as hydrazines. In this case, because we have an electron-rich nitrogen adjacent to our nucleophilic nitrogen atom, imine formation can occur quite readily. You'll see a wide number of hydrazine derivatives. The most common that we see in the organic laboratory is the 2,4-dinitrophenyl hydrazine derivative. Other examples include hydroxylamine derivatives, where these can also be used to form stable isolable imines. Looking at 2,4-dinitrophenylhydrazine, it reacts readily with ketones and aldehydes to give 2,4-dinitrophenylhydrazones, which are a class of imine derivative. These are very useful because they're solid products and they can be useful to help characterize liquid ketones and aldehydes using their melting point. We, in fact, in this coming lab, will isolate cinnamaldehyde, prepare a hydrazine derivative. In this case, rather than making a formal hydrazine derivative, we make a semicarbazole derivative, and then we measure the melting point. Now, let's show a mechanism for this reaction, just so that way we can review our mechanism for imine formation and we can understand this really useful reaction that we're utilizing heavily in our future laboratories. So the first step for So the melting point depends heavily on the substitution and the overall molar mass and polarity and other structural features of your parent ketone. So different ketones will generate different hydrazone derivatives, each with their own melting point, boiling point, IR spectra, and all the physical properties associated with an isolable crystalline solid. Did that answer your question? So the first step in this mechanism, under acidic conditions, which is textbook for enamine formation, we will protonate our ketone, or aldehyde for that matter. And from here, we generate a much more electrophilic carbonyl derivative. From here, our nucleophile, I'm going to abbreviate this aryl group as R, just to showcase this is a very general mechanism. From here, our nucleophilic amine nitrogen will attack the electrophilic carbonyl carbon. From here, there is going to be a series of proton transfers. And we will be able to isolate and observe our imine after loss of water. So after our proton transfer, we now have set up our substrate to kick out and lose this wonderful leaving group, water. That in turn gives us our iminium ion. And for our last cleanup step, we're just going to deprotonate the iminium ion to give us our neutral isolable imine. The acid doesn't necessarily have to be a halogenic acid. Other common acids used are toluene sulfonic acid, though hydrochloric, hydrobromic, hydroiodic acid are just cheap, readily available sources of H+. Does that answer your question? Any other questions that I can address? Okay, let's keep going then. And let's try to apply what we've learned here. In this case, we're asked to predict the product of the following reaction and then draw a mechanism for the following reaction. So in this case, we have a ketone and an allylamine, and we have trace amounts of acid. So what product will we observe? And most importantly, what is the mechanism for the formation of this product? Keeping in mind that this amine is a primary amine. So let's take a few minutes and let's work through this problem. And then I'd like students to share their responses in the chat or verbally for the proposed mechanism and the structure of the product. And if possible, I'd like students to annotate and share their proposed responses either as a photo of their written work in the chat or annotated directly onto the class whiteboard using the annotate tool.
I have a question, Professor.
Yes.
So is it only primary because the carbon with a double bond to the O is primary?
No, I mean, I'm saying the amine is primary
Oh, I mean,
because
sorry.
the amine only has one alkyl substituent.
Yeah, okay, thank
Does
you.
that make sense?
Yeah, thank you.
Perfect, perfect. So in this case, our acid source will be H3O plus, just a generic source of aqueous acid. So would anyone like to walk us through the steps for this mechanism or share their annotations for this proposed mechanism? So we have a student starting to annotate their proposed response on the class whiteboard. So our acid in the first step will protonate our carbonyl oxygen. Perfect. Now that we've protonated our ketone carbonyl, we've now activated our carbonyl for nucleophilic attack. Conveniently enough, we have a nucleophile already ready to go, and our primary amine so our primary amine will attack our carbonyl carbon, and we generate a tetrahedral intermediate. From here, in order to activate water as a leaving group, what's the next step in this process? So we have a protonated amine currently. So our goal would be to protonate the alcohol to activate it as a leaving group, and to make our amine, to free up a lone pair on our amine to lose water, we need to also deprotonate the amine. Yeah, if we had too much acid, if we use an excess rather than catalytic, this reaction wouldn't be very efficient because a protonated amine is a way less effective nucleophile. It's much less nucleophilic. So after the proton transfer, we've now activated water as a leaving group. And so from here, we can kick out water and generate an iminium. Now, this iminium isn't inherently easy to isolate. Rather, it's often more efficient to isolate the neutral imine after a quench or wash. So in order to get a neutral, easily isolable species, what's the next step? So after deprotonation of our iminium, that gives us our neutral imine. Yep, this student proposed mechanism looks completely reasonable. So let's just re-annotate this student proposed mechanism, just so that way we have everything saved when we post the final note set. Okay, so the first step in this process is to activate our carbonyl via protonation. Now that we have an activated carbonyl, our carbonyl carbon is now substantially more electrophilic, and as such, it can be attacked with nucleophiles such as the amine present in solution. After addition, we have the following tetrahedral intermediate. And in order to activate this tetrahedral intermediate, we're going to have to engage in a series of proton transfers. So we'll protonate our alcohol to activate our leaving group, and we'll deprotonate our ammonium ion to free up a lone pair. From here, we're now all set up and ready to lose water as our leaving group and form our iminium ion. So we're going to kick out water via 1,2 elimination, and that will generate our iminium ion. Now, as you notice, this is a non-neutral species. So to get a neutral isolable species, we'll deprotonate our iminium ion with water. And that gives us our final imine product. Does this example make sense to everyone? Any questions on this example? Any questions or points of clarification for this example?
I kind of missed the first couple minutes of class. Is amine just a nitrogen that's double bonded, or like what?
So an imine is this following motif where we have a carbon-nitrogen double bond.
Okay.
This structure is known as an imine. Imines form preferentially when we react a ketone or aldehyde with a primary amine. Does that answer your question?
Yeah. Would pyridine be?
So pyridine wouldn't work for these reactions because first it's non-primary, and the second reason stems from its substitution pattern and the substitution of the nitrogen. So this wouldn't function as or wouldn't be practically useful for imine or enamine formation, although cyclic amines are usable, but because pyridine is part of an aromatic ring and due to its substitution pattern, it's not able to form this requisite iminium intermediate nor form an imine because that would result in substitution beyond the octet. Does that answer your question?
Yes, it does. Thank you.
Perfect. Any other questions on this example? It wouldn't be correct to call pyridine an imine necessarily because an imine typically implies that it's reactive at the carbon center and it's electrophilic at that carbon center. Pyridine is closer to that of a heterocycle, and thus it doesn't react like your typical imine or enamine. Does that answer your question? Perfect. Okay, so we've seen the mechanism for imine formation. Now let's talk about enamine formation. So the first step in this process is almost identical to previous steps. So the first thing that's going to happen is we are going to activate our carbonyl. So let's show this activation step. I find when you look at the mechanism in the book, they sometimes like to bundle steps together. So we have our acid source. Has to be a pretty strong acid. And we reversibly generate our protonated carbonyl. From here, we have a much more electrophilic species. And our nucleophile, which in this case, let's redraw our nucleophile. Rather than a primary amine, we're looking at what happens when we have a secondary amine. And the moment you see a secondary amine, I want you to think we're going to form an enamine over an imine. So we're going to attack our carbonyl just like normal, and this generates a tetrahedral intermediate. From here, just like before, we have to activate water as a leaving group and deprotonate our nitrogen. So water is going to come on in and pull off a proton, and our acid will donate a second proton. So we've activated water as a leaving group, and we've freed up a lone pair on nitrogen. Yes, secondary amines will form an enamine. Now that we've freed up this lone pair, we can kick down our lone pair and lose water. And that in turn generates our Iminium Ion. Now, would someone like to tell me what is special about this Iminium Ion? What is unique because we have a secondary amine? Can we get a neutral isolable species by deprotonating this Iminium Ion directly? Is there a hydrogen still attached to our nitrogen? No. So in order to get a neutral isolable species, instead we abstract an alpha proton, and that in turn forms a carbon-carbon double bond and breaks our carbon-nitrogen double bond to give an enamine. So the reason why secondary amines give an enamine is the only way to get a neutral isolable species from your iminium intermediate is by deprotonation at the alpha position. One other consideration that I'd like you just to think about is when you think about this iminium ion, and we just take a look at this iminium ion. We have this pretty congested alkene, right? Looking at this alkene, would we agree that there's a fair amount of steric strain on this alkene? We look at this carbon-nitrogen double bond, and we have these two R groups on our amine, our two R groups associated with our ketone or aldehyde. Would we agree that there's a fair amount of steric strain by having this highly substituted alkene? Certainly, right? So another motivating factor in order to form an enamine is to minimize this steric strain. This is a common theme associated with enamines. And the reason why I bring this up, the reason why I'm talking about this is I really want to introduce this idea that enamines and imines are sensitive to steric strain. Now you may say, how is this useful? Well, if we have a ketone where we can form an enamine at either site A or site B. So let's suppose we're reacting this ketone with dimethylamine, okay? So we could get one of two sets of enamines that we'll call A and B. Now, if we think a little bit about the fact that these enamines are going to be flat, they're sp2 hybridized, this bond angle is 120 degrees. Which of these structures has more steric strain? Which of these structures is more congested? Which of these structures has a more crowded and strained alkene? And to help everyone visualize this, let's just draw a rudimentary picture. So in the first case, we have our methyl group, and our methyl groups on our amine are pretty close to our hydrogen. Okay? This isopropyl group is free from this planar system. If we look at structure B, we have this highly substituted alkene. And if we were to look at it from a 3D perspective, you're going to begin to see the problem almost immediately. Now, because we have an alkene, and because this nitrogen is now snapped into the plane of the page, it's now held almost flat because it's part of the enamine, we now can see pretty quickly what's happening between these two groups. What's happening between the alkyl group of our amine and the alkyl group of our ketone. Looking at this picture, do we see how they're bumping into each other? Do we see how there's a lot of steric strain in this second structure? So then, with these pictures as context, which of these two enamines would we expect to be more strained? Which of these enamines are more strained? B, exactly right. It's a highly strained enamine. And as a consequence of this, when you form enamines, you see only the least hindered, least substituted enamine form. The least hindered, least substituted enamine forms. Now, the reason why this occurs, for those who are curious, and I'll talk about it now, stems from the fact that when we have this orbital overlap, right? This is our orbital overlap associated with this conjugated system, right? Now, due to this strain, due to this steric strain, we end up having to rotate our bonds to minimize this strain. And as a result, when you have these strained enamines, you end up interfering with this conjugation and you lose some of this stabilization due to resonance. This is quite an interesting effect where essentially the strain causes distortions in your bond angle, which weakens this overlap, which in turn leads to a less stable enamine overall. Does this answer your question? Now, I know that was a lot of background just now. The main thing I want you to keep in mind, enamines are very sensitive to strain, and enamines form to give the least hindered, least substituted enamine to minimize these steric repulsions. This is a useful method to prepare easily and under relatively mild conditions a kinetic enolate equivalent. We'll talk more about the application of enamines later on in this course. So, for now, let's just recap here. Is everyone comfortable with the mechanism for enamine formation? When we have a secondary amine, our iminium ion cannot be directly deprotonated at nitrogen. So we deprotonate at the alpha carbon to make an enamine. Any questions on that before we try to apply what we've learned?
So is the difference between secondary amine and an enamine is the fact that instead of a hydrogen, it's a carbon? Or is there anything that has to do with the alkene?
So an enamine specifically refers to a nitrogen directly conjugated to a carbon-carbon double bond. And an enamine, if we think about sort of resonance contributions, is very electron rich at this alpha carbon. So it can actually function as a competent nucleophile. And we'll see examples of enamine reactivity in later chapters when we start to talk about enolates and other carbon nucleophiles. Does that make sense? Did that answer your question?
Yeah, thank you.
Perfect. So let's try to apply what we've learned here. And let's try to predict the product for the following reaction and draw a mechanism for the following reaction. This carbon skeleton, let's see. So your first thought was that a base would more easily pluck a proton from the less substituted site. That is also an argument that could be made, although enamine formation and imine formation for that matter is reversible. So it's beyond just a strictly kinetic effect. Did that answer your question in the chat? But your argument is the textbook argument for why a kinetic enolate forms. It's the least hindered site to remove a proton. But as we see in a lot of these mechanisms, imine and enamine formation is reversible. It's an equilibrating process. And as such, you will get the enamine that is favored accounting for primarily thermodynamic effects. So issues of strain and which of these two enamines is more stable, accounting for these strain and resonance effects. Okay, so we have an example where we're asked to predict the product of the following reaction and draw a mechanism. So in this case, we have a secondary amine. So what does that tell us immediately? Secondary amine, acidic conditions, and we have a carbonyl. What are we going to make? An enamine, yeah. Does anyone recognize this ring motif? There is a substantial amount of research in into proline enamines, and they're commonly used for enantioselective variants of these reactions. And this ring system shows up a lot in proline and other related chiral amines. Okay, so with that said, let's take a few moments and let's try to draw out a mechanism for this reaction and predict the products from this reaction, remembering that the enamine forms on the least substituted position. So let's take a few minutes, and then I'd prefer students to share their responses in the chat, verbally, or annotated directly onto the class whiteboard. And it's almost like twofold practice because the mechanism for enamine formation mirrors that of imine formation. So would anyone like to share their proposed responses annotated on the class whiteboard? So in our first step, we're going to activate our carbonyl via protonation. Now that we've protonated our carbonyl, we have a much more electrophilic carbonyl carbon. And our electrophilic carbonyl carbon can then be attacked with a range of reasonable nucleophiles. So in this case, our amine will quickly attack the electrophilic carbonyl carbon, and we'd get a tetrahedral intermediate. Now that we have this tetrahedral intermediate, we're going to, again, need to activate our alcohol as a leaving group. And the easiest way to do that would be what? What's the easiest way to activate our alcohol as a leaving group?
Sorry, I'm slow.
Oh, no worries at all. I'm just asking the chat as well, just for having a class dialogue while a student is annotating. Protonation, exactly right. So as the student's drawn, we'll protonate our alcohol. One thing I noticed is that your amine lost a proton during the addition step. Would you be able to show how that proton was removed? Notice how we went from NH to just nitrogen. That is what's happening in the mechanism, but we just need to show that loss of a proton using water or another base. Yep, exactly right. Water removes a proton from our ammonium species. From here, now that water is activated as a leaving group, we can kick out water and make an iminium. However, this is where things get a little bit interesting. This is where things get quite interesting. In this case, because our amine is secondary, our iminium intermediate cannot be directly deprotonated. So then, to get our enamine, what do we have to do? And pretty importantly, which proton will we remove? The left or the
Wait,
right? Oh,
you said deprotonated?
well, I would start the mechanism that you drew so far is perfectly fine. You get an iminium, right? And
Okay.
the arrows that you've drawn look great. Would you be able to draw that iminium?
So would it just be like double bonded
Yep,
here?
exactly right. And as we notice, because nitrogen has 4 bonds, it's positively charged. So this is known as an iminium. Yep. So then, and now this is an important juncture. We can't just pull off a proton from our nitrogen. There are no protons to remove, right? However, we have alpha protons, protons on our adjacent carbons. And these are the carbons adjacent to the iminium carbon. So then, we can remove a proton to get our enamine, and which proton will we remove? So I'll label them A and B. Which proton will be removed to make our enamine?
I would guess B.
Yep. And would you be able to provide a reason for that?
Because it's less substituted.
Yep, exactly right. And enamines are especially sensitive to steric hindrance, and they generally form on the least substituted position. Perfect. And this student proposed mechanism looks completely reasonable. Thank you everyone who also shared your proposed comments and answered questions in the chat. Now that we have as a class have arrived at the complete mechanism, let me just clear those annotations and redraw the mechanism for our reference. The reason why you don't form an enamine inside your ring or using the alkyl groups attached to your amine, it's not just due to strain, it's also due to electronic effects. And we'll talk about that in a moment. So the first step in this process is that we are going to protonate our carbonyl. That activates our carbonyl carbon, making a much more effective electrophile. From here, our secondary amine will attack our electrophilic carbonyl carbon, and that in turn gives us a tetrahedral intermediate. From here, we're going to activate water as a leaving group via protonation. And we're going to deprotonate our ammonium species to free up a lone pair on nitrogen. From here, we now have water prepared as an activated leaving group. and we have an available lone pair on nitrogen. We can kick that lone pair down to lose water, and we have our textbook Iminium Ion. Now, unfortunately, we cannot just remove a proton from our nitrogen. There's no proton to remove. It's a secondary nitrogen. It's a second. Let me rephrase that. It's a secondary amine. There are no hydrogen atoms present on that nitrogen after addition. So we can remove one of our alpha protons and in turn kick that electron density back to our nitrogen atom. You can't remove protons within, you can't remove a proton from the carbons adjacent to nitrogen because that wouldn't give you the right distribution of electron density. You wouldn't actually be kicking any electron density to nitrogen, right? Does that argument make sense? Perfect. So we remove the least hindered proton to give the least substituted enamine. And that's because enamines are highly sensitive to steric strain. And if you were to try to form the more substituted enamine, you'd be introducing a lot of destabilizing steric interactions and be interfering with the stabilizing orbital overlap for this conjugated system. So, with that said, we were able to predict the product from this reaction, and we're able to show quite clearly that when we have a secondary amine under acidic conditions, they react specifically with ketones and aldehydes to yield enamines rather than imines. Any questions on these examples? Any other questions before we move on to the next examples? Okay, let's keep going then. Now, similar to acetals, imines and enamines can be hydrolyzed under aqueous acidic conditions to regenerate the aldehyde or ketone. Okay, so let's look at an example where we have an imine and we are hydrolyzing that imine. So it's just like the mechanism to form an imine, but in reverse. So in order to activate our imine carbon, we're going to protonate our imine nitrogen. We've now activated the imine. It's now a much more effective electrophile because we now have an iminium ion. From there, water will attack the electrophilic imine carbon. And we get a tetrahedral intermediate. However, this time we have an entirely different goal in mind for this tetrahedral intermediate. In this case, we need to activate our amine as a leaving group, and we're going to accomplish that via protonation. So we're going to protonate our amine, and we are going to deprotonate our alcohol. That in turn gives us this activated ammonium species, which is a much better leaving group. We have our alcohol, and now we can kick down our lone pair and lose our leaving group. And that in turn gives us our protonated ketone, which we can then just deprotonate with water. And that in turn gives us our desired ketone after hydrolysis of our imine. Does this mechanism make sense to everyone? Does everyone notice how it's just the same mechanism for imine formation in reverse? Any other questions that I can address on this example? Okay, so let's keep going now. And I'd like us to try and draw the mechanism for the hydrolysis of an enamine now. Remember, enamines are pretty electron rich at the alpha carbon position. So let's take about 3 to 4 minutes, and then let's try to draw out a mechanism for the hydrolysis of an enamine, keeping in mind that it is almost the reverse steps to make the enamine. So let's take a few minutes to work on this example, and then I'd like students to share their questions or proposed responses in the chat, verbally, or using the annotate tool. And of course, if you have any questions on this example, do not be shy to ask them in the chat or verbally as we work through this example. So, would anyone like to share their proposed mechanism as a photo in the chat? Does anyone have any comments as we work through this mechanism? Or would anyone like to share and annotate their proposed mechanism on the class whiteboard? Or if you have a question, does anyone have a question that would help advance our discussion?
Do we need to move the double bond, or can we just kind of do it from there?
The double bond doesn't need to be directly removed, but I'd like you to note that that double bond is very electron rich. And as a result, you can, just like we deprotonated the alpha position to make the enamine, what happens if we take an enamine and we treat it with strong acid? What position is very electron rich that would be protonated then?
The carbon, the ending, or the terminal carbon?
Yeah, we call this the alpha carbon. Yeah, because it's the carbon directly adjacent to our carbonyl-like functionality. And yes, that's exactly right. Just like we can deprotonate the alpha carbon protons, we can protonate at the alpha position in our hydrolysis mechanism. Would you be able to draw that? Or would you be able to draw a rough annotation of what that protonation step would look like? Or would a student, or any of the students for that matter, be able to or want to annotate that protonation step? Since I think once we get that protonation step complete, we start to see something that looks a lot like an imine, and then we can use the same mechanistic steps that we used for the imine hydrolysis mechanism. Okay, so we know that the alpha position of our enamine is very electron rich, and you can say even that position is pretty basic. So then if we treat our enamine with strong acid, how would it look like from an arrow pushing perspective if we're protonating that alpha position? So I see someone annotating H3O plus. Now we just need a set of arrows to show that protonation step. We can protonate nitrogen, but the nitrogen isn't actually the most electron rich position in this structure. Yep, the alpha position is. So the nitrogen is kicking its lone pair down, and that facilitates protonation of the alpha position using this electron-rich alkene. Does this idea make sense to everyone? How enamines are very electron-rich, and by resonance, looking at the distribution of electron density in the enamine, you can protonate at nitrogen, but the carbon is actually more reactive and more electron-rich. It's not a bad first idea, and in fact, that's one pathway, though it's not productive. Once we've protonated our enamine, does that iminium look familiar to everyone? Do we have the tools now to hydrolyze that iminium? Would anyone like to try to annotate out that hydrolysis step? And I would like to say there's plenty of space on the class whiteboard. So if multiple students would like to share their annotation, or if students would like to comment on the steps for this mechanism, I would highly encourage you to do so. There's a lot of value in even just practicing drawing out the mechanism. So the iminium, super reactive as an electrophile. Water, even though it's not the best nucleophile, it will definitely go and attack your iminium ion carbon. So now that water has attacked our iminium ion carbon, we're going to deprotonate water. And now we still have to activate our amine as a leaving group. Would anyone have a suggestion? How do we activate our amine as a leaving group? Do we have any comments in the chat? Nitrogen gets protonated, yep. And then I see someone in the chat typing the next step where the oxygen lone pair is going to be used to kick out our ammonium ion. So now that we protonated nitrogen, we have a much better leaving group. So then our lone pair on oxygen can be kicked down. We lose our amine. And all we have to do now to get a neutral isolable species, to get our neutral isolable ketone, is to just deprotonate our oxygen. Yep, so this student proposed mechanism looks completely reasonable. So let's clear the annotations and let's redraw and discuss this mechanism. So as we talked about previously, enamines are very electron rich at the alpha carbon position. And as such, during protonation, you would directly protonate the enamine carbon. And that would give us our iminium ion. This iminium ion is a highly reactive electrophile, and it can be attacked readily with nucleophiles such as water. Water will attack our iminium ion. And then from there, that gives us our water adduct. Now, we still have to activate our amine as a leaving group and free up a lone pair on oxygen. So we're going to deprotonate our oxygen atom and then protonate our nitrogen. Now that we've activated our amine as a leaving group, and we have an available lone pair on oxygen, we're going to kick the lone pair down, and that in turn gives us our protonated ketone, which can be readily deprotonated to give a neutral isolable species via deprotonation with water. Does this mechanism make sense? Any questions on this example? Okay, let's keep going then. So we have another case where we're asked to predict the product for the following reaction and draw a mechanism for the following reaction. So would another student volunteer like to take a few moments, let's take about 3 to 4 minutes, and let's try to draw the mechanism for the hydrolysis of the following iminium ion. No worries. Don't be too shy to annotate your responses, even if you participated previously. I just wanted to open the floor for if someone else wants to try to practice. I find the act of drawing out a mechanism and putting pen to paper is invaluable at both practicing the act of drawing mechanisms and helping clarify any questions that you may have. So would another student volunteer like to try to draw out or talk us through the steps for this hydrolysis mechanism? Let's work through this problem over the course of about 3 to 4 minutes. And I'd like students to share their responses in the chat verbally. You can also send a picture of your written work in the chat, or you can ask questions in the chat or verbally.
Would we do protonation of the nitrogen for this one?
So in this case, the nitrogen is already fully substituted. So it's already activated and ready to go. So this is an iminium ion. But yes, for most imine hydrolysis mechanisms, you would protonate nitrogen. And now that we have this activated species, this iminium ion, what happens next? What's the next step if we have a lot of water floating around? A lot of a nucleophilic solvent, one could say.
So the water will attack the double bond
Yep.
carbon.
Yes, and it will attack the iminium ion carbon. Would someone like to draw that out? Would
I
someone,
could draw it, but if someone else wants to do it, go ahead.
would anyone else want to volunteer to draw it out? I find practicing actually drawing out the arrow pushing is invaluable. No worries, no worries. That's more than okay. It allows us to discuss as well. So don't be shy. There's plenty of space on the class whiteboard. So if students would like to annotate, doesn't matter if it takes you a little bit to annotate. I certainly know it's cumbersome annotating with the mouse, but it would be good to just give students an example to showcase those steps.
So for this one, we can just directly start with the water is pretty much what you're saying versus.
Yeah, exactly, because we're already at the iminium ion. Yeah.
Oh, makes sense. Thank you.
So if anyone would like to annotate that step where water attacks our iminium ion, don't be shy. And this will be open to anyone who'd like to annotate. And of course, I'd re-annotate as we advance through our discussion.
So is the water attacking like a bond adjacent to that double bonded carbon? Is that what's going on?
In this case, just to re-annotate what the students drawing, they're showing the attack onto the electrophilic iminium carbon.
Okay.
So let me re-annotate what the student has shared, just so that way we're all on the same page as we go through this mechanism. So we drew out the first marquee step in this route, which is the attack of our nucleophilic solvent, in this case, water. Onto our highly electrophilic iminium ion carbon. From here, we now have the following tetrahedral intermediate. So let's continue this mechanism from here. What's the next step? So would anyone like to try to share the next step? So we have one student mentioning we protonate the nitrogen and deprotonate the oxygen. Okay, and we have someone starting to draw out our protonation and deprotonation steps.
I give up.
No, it's good. It's good. It's good. Just one. I would just draw the lone pair. Would anyone else like to help out to help complete those 2 arrow pushing steps? Don't be shy. There's plenty of space on the class whiteboard. Okay. Perfect. Perfect. So we're deprotonating our oxygen atom, and then we are protonating our nitrogen atom. Perfect. Perfect. So let me re-annotate that. So to activate our amine as a leaving group, we're going to make the ammonium salt. And to free up a lone pair on oxygen, we're going to deprotonate our oxygen atom. And that gives us the following intermediate. Now that we have this activated ammonium species, what is the next step? What happens next if we're hydrolyzing off our imine? Yep, exactly right. We kick the lone pair down and we lose our activated leaving group. Yep, exactly right. Now we have our protonated ketone. And then what's our last cleanup step? Perfect. Yep, we deprotonate our ketone to give a neutral isolable product. Okay, so let's showcase that last step, just re-annotating that last step. And that in turn gives us our final product. Does this example make sense to everyone? So, any questions on today's lecture before we archive today's recording? Any questions on today's lecture? If we don't have any other questions, what we'll do is we'll archive today's recording.